Hello everyone. So in this lecture, we will try to analyze a given problem, which is we will try to understand this reg to reg path, and we will explore different concepts in this problem. So let's start. So this particular path is a clock path, and this particular path is data path. Then we have ubuff5, which is common to both launch path and capture path, and UFF0 is a launch flop and UFF1 is a capture flop. So this is how this path looks. So I am removing this. Okay, so let's suppose that for PCLK we have a rise transition and fall transition defined in SDC. So out of this, which transition has to be considered while calculating the delay of ubuff5 and all the downstream logic? Okay, so we are considering the clock path first. Okay, so here this UFF0 is a rising edge triggered flop, so this will have a rising edge, and if we backtrace, because this ubuff5 is a buffer, where this is a buffer, so it is a positive unit. So of course, the if input is rising, the output is rising, or output is rising, then input is also rising. Similarly for capture path, so since we are having a rise transition over here, so of course due to the interconnects, it will experience some slew degradation. So we have a rise transition over here as well, and we have some rise transition over here. So for all these gates, we will only consider the rise delays because we don't have the possibility of using fall delay in this case. Correct? Because in dot libs, we are having both rise delays and fall delays. So in this case, since we have the transition like this, so we will have only rise delays cal calculated from the dot lib. So next, now come to the data path. So if you see in the data path, so how the transition on the Q pin is decided. The transition on Q pin is decided with the help of the D pin. So if the D pin is rising, the Q pin is also rising. If D is falling, then Q is also falling. And then the transition of all the downstream logic will be calculated accordingly. So in first case, we will consider, let's say the D is rising, okay, because we don't know the transition. So we consider the low to high transition or rise transition over here. So Q will be rising. So over here, this will be a transition. And now talking about this NAND gate, how to calculate the transition, because we don't have any information about this particular pin. So let's assume that this is 1. If this is 1, so let's say y is equal to a dot b bar. So y is equal to If A is 1, then Y is equal to B bar. If B is 1, then Y is equal to A bar. So this says that output of this NAND gate is invert of the input. So if this is rising, so this is falling, correct? We also consider this is an AND gate. So if we consider the 1 over here, so this will have, because this is a AND gate, so Y is equal to A dot B. So if any input is 1, then Y is equal to V. V. It act as a buffer, correct? So if it act as a buffer, so it will have a fault transition over here. It will have fault transition over here. So this is how the transitions are seen. Now a question can come that why did I consider 1 over here, not 0? So let's try to do that also. So instead of considering 1, let's consider 0 over here. Now, if we consider 0 over here, the output of this NAND gate is 1. And if we consider, let's say 0 or 1, then it will have 0 or 1 in the output. So can we calculate the delays in this case for this particular NAND gate? No, because we don't have the edge in the output. So it is not logical. So we can also see this information from the dot-lib. So here I have a snip of any generic NAND gate. Okay. So it is having two input pins A, B, and Zn. This is a NAND gate. So Zn is equal to A dot B bar. Okay. So we go to the timing section, and here if the related pin is 1, so we are talking about the A pin. When B is 1, so when B means when B is equal to 1. So when B is equal to 1, any transition, that is rise or fall transition, will lead to fall transition and rise transition over here. So because this is a negative unit, correct? So similarly for other case, so when A is 1 and B is a variable, that is C is low to high transition, high to low transition. So this will follow a negative unit. So this will have high to low and this will have low to high. So that's why it's a negative unit. So is there any case over here with A0? So A0 means there should be a condition like when A not like this. So there is no condition over here when A is 0. So this is quite expected because when A is 0, we will not see any edge in the output. It is a constant value. So there is no logic of finding the transition or delays. It cannot be calculated. So let's say if we are having a 0 over here, if we consider a 0 over here, so it will not be able to find the timing through this path because there is no such arc present from A to, so let's say A to Z when B is 0 because there is no such arc. So the timing tool will not be able to calculate the timing through this path. So it will not report any path, any timing between this path. So this has to be 1 for the NAND gate. So this is how it works. So this case, what we saw, let me draw again. Here, this is a negative unit. So this is falling, and then this is also falling because this is a positive unit gate. And so this is how the transitions look. Now, another case may be when D is actually falling. When D is falling, the Q is falling, and the output of this NAND gate has is rising, and this is rising because this is a positive unit. So this is how we we are able to find the transition of the gates, correct? So this is one thing. And now another point about like how the transitions are calculated actually from the dot lib. So first of all, we discussed that how the direction of the transition are taken care, and now we will see that how the transitions are calculated from the dot lib. Okay, so as we saw that we have to consider a rise transition for PCLK. So ho- how do we calculate the transition at the output pin of UBUF5? So it's of course a function of input transition and output cap. So it will have the input transition value and output load value in a form of lookup table, and it will be able to find out the transition in that. How the transition of this flip-flop will be decided at Q pin. Okay, so I have the example of flip-flop. Okay, so we will see the Q pin over here, which is the output pin. So we'll see the timing section, and if so, this is the rise transition. So rise transition or rise slew is calculated with the help of this table. Okay, so we will have a lookup table over here, which is a 2D table. Okay, so we will have these values till 0.10 and 0.01 to 0.10. So it will calculate the transition with respect to this. And index one is input slew. And what is input slew? Slew of a slew of a clock, that is clock skew, and Q slew, that is output slew. So this is how the transition for the flip-flop UFF0 will be calculated. Then comes the transition for NAND gate. Okay, so we will go inside the NAND gate. So transition in the output. Okay, so here we have, let's say if this pin is A, okay, so it will see A to Z. So this is the arc from A to Z, and it will see the fall transition over here. It will see the fall transition over here. And we will have these values as in the form of a lookup table as we saw just now. Similarly, for NAND gate, it is also a function of input transition and output cap. So this is the concept about the transitions. And regarding the clock path, the transition are fixed because uh, we have rising edge launch flop and rising edge capture flop. So it is fixed. We need not to consider two different cases as we did over here because launch flop is a positive edge triggered and capture flop is also a positive edge triggered flop. So this is all about the transition. So we will talk about the delays in the next video. Thank you.